Hey everybody, welcome back to Trigonometry. Today we're in section 2.1 and we're talking about the trig functions of acute angles. In this section we will learn the right triangle based definitions for the trig functions. We will also talk about cofunctions and we'll learn the cofunction identities. And very importantly, we will learn the trig function values of the special angles 30, 45, and 60. So here we go. We're going to start by restating the definitions of the trig functions. So far, all of our trig function definitions have used x, y, and r, and we depended on the angle being in standard position. So using the x, y, and r definitions, we could find the trig function values for angle A in this diagram, but not for angle B because angle B is not in standard position. So instead of using x, y, and r, if we restate the trig functions in terms of how the sides are related to the angle we're interested in, we'll be able to find the trig function value for any angle in any position. So let's take a look at this diagram, and we'll start with angle A because we're already used to finding the trig function values for the angles that are in standard position. So we've always talked about the horizontal side being x, the vertical side being y, and the hypotenuse being r. But we could also say that this side of length y is the side opposite from angle A. And we could say that the side of length x is adjacent to angle A. And of course, we know that the side of length r is the hypotenuse. It's also adjacent to angle A, but we don't call this side adjacent because it's the hypotenuse. The terms adjacent and opposite only apply to the legs. So now let's go ahead and restate our function definitions. Let angle A represent any acute angle in standard position. Then according to what we already know, the sine of angle A is y over r, but we can now restate that as opposite over hypotenuse. So the sine of angle A is opposite over hypotenuse. The cosine of angle A we have always known as x over r, but now we'll call this side of length x adjacent. So the cosine would be adjacent over hypotenuse. And then the tangent of angle A we know is y over x, but we can now state that as opposite over adjacent. The three reciprocal functions work just the same. So the cosecant of A would be r over y, but we can now state that as hypotenuse over opposite. Secant of A would be r over x, but we can now state that as hypotenuse over adjacent. And cotangent of A would be x over y, but we can now state that as adjacent over opposite. So it's just as important to know these right triangle-based definitions as it is to know the definitions that depend on x, y, and r. So let's practice a little bit. Here we have a right triangle, and we have not a coordinate system in sight. But the instructions say find the sine, cosine, and tangent values for angles A and B in the figure. So let's start with angle A. And so if we're looking at angle A, then we can identify the side opposite, the side adjacent, and the hypotenuse. And so the sine of angle A we know is opposite over hypotenuse. So that would be opposite, which is 7, over hypotenuse, which is 25. And then the cosine of angle A would be adjacent over hypotenuse. So coming from angle A, that would be 24 over 25. So coming from angle A, the side adjacent would be the 24, and then the hypotenuse is 25. And then for the tangent of angle A, we know that's opposite over adjacent. So that's going to be 7 over 24. And now let's do the same thing for angle B. So this time we have to figure out what sides are opposite and adjacent coming from the perspective of angle B. So when we look at angle B, the opposite side is the 24 and the adjacent side is the 7. So the sine of angle B again is opposite over hypotenuse, but this time the opposite side is 24. So the sine of B is 24 over 25. The cosine of B is adjacent over hypotenuse, but this time the adjacent side is 7. So the cosine is going to be 7 over 25. And the tangent of angle B will be opposite over adjacent, so that's going to be 24 over 7. So notice here that the sine of angle A is the cosine of angle B, and the sine of angle B is the cosine of angle A. That's not a coincidence. It couldn't work any other way, could it? Because the only three sides that we have to deal with are these three, and so what's opposite for one angle is going to be adjacent for the other angle. So you can see how the values trade. Now, in some problems, we'll be required to draw our own right triangles based on a verbal description of the triangle. So they might give you the length of both legs, or they might give you the length of the hypotenuse in one of the legs. And in these problems, if the sides and angles are not labeled correctly, then you won't be able to find the function value that they're asking you to find. So here's how we're going to do it so that we get the expected answer every single time. In a right triangle, the angles are always labeled with capital letters, and the sides are always labeled with lowercase letters. So look at the diagram that we have right here. We've got our right angle clearly marked. We've got our angles labeled with capital A, capital B, and capital C. And then each angle in the side opposite to that angle must be labeled with the same letter. And so we're going to take angle A and look for the side opposite to that, and that should be labeled lowercase a. And then for angle B, the side opposite to that should be labeled with a lowercase b. And for angle C, of course, the side opposite that is the hypotenuse, and that should be labeled with a lowercase c. And you'll remember from section 1.3, we talked about how when we're using A, B, and C, the letter C is always reserved for the hypotenuse, and that means that the letter capital C is always reserved for the right angle. Now let's look at example 2 together. It says, suppose ABC is a right triangle with sides of lengths lowercase a, lowercase b, and lowercase c, and right angle at capital C. Given that side B is 24 and side C is 26, sketch the triangle, label all the sides and angles, and find the sine of angle A. So let's start by just drawing a right triangle. Now we know that the right angle should be labeled capital C, and we know that the side opposite to that, which is the hypotenuse, should be labeled lowercase c. After that, it does not matter which of these we choose to call angle A and which we choose to call angle B. So I'm just going to call this one A. But now that I've labeled this angle as capital A, the side opposite to that must be labeled lowercase a. And the last angle that we have to label is capital B right here. And that means that the side opposite to that has to be labeled lowercase b. Now they've told us in the problem that B is 24 units long and C, the hypotenuse, is 26 units long. So now we've sketched our triangle, we've labeled all the sides and angles, and now we want to find the sine of angle A. So we know that the definition of the sine of A is opposite over hypotenuse. And so for this triangle, that's going to be A over C. Now, of course, we don't know the length of side A yet, so before we can finish the problem, we'll need to use the Pythagorean theorem to find the length of the unknown side. So we know that this is a leg, and we know that whenever we want to find the length of a leg in a right triangle, we subtract the squares. So we're going to be subtracting c squared minus b squared. So a squared now is going to be 26 squared minus 24 squared. If you evaluate that on your calculator, you'll find that a squared is 100, and that means that a is 10. And so now, if we know that the sine of angle A is the length of side A over the length of side C, we know that's going to be 10 over 26. And this fraction can be reduced because both of these numbers can be divided by 2. And so we find that the sine of angle A is 5 over 13. Now, if you think back to example 1, you'll remember we noticed that the sine of angle A was equal to the cosine of angle B, and we said that that was not a coincidence. So now we're going to take a little closer look at how this works. So what we're going to do here is take each of these ratios and figure out what trig function this ratio represents for angle A and what trig function it represents for angle B. So first, let's start with angle A, and let's think about A over C. So if we're coming from angle A, then A over C would be opposite over hypotenuse, and we know that opposite over hypotenuse is the sine function. But if we're coming from angle B, A over C would be adjacent over hypotenuse, and so that would make it the cosine of B. So A over C is the sine for angle A, but it's the cosine for angle B. And now let's think about the ratio A over B. So if we come from angle A, then A over B is opposite over adjacent. So that's going to be the tangent function for angle A. But if we come from angle B, then A over B is going to be adjacent over opposite, and that's going to be the cotangent function. And our last ratio is C over B. Now this one will probably be the hardest to recognize, but we can do it if we just remember our reciprocal identities. So coming from angle A, C over B would be hypotenuse over adjacent. Now that's the reciprocal of cosine, because cosine would be adjacent over hypotenuse, but here we've got hypotenuse over adjacent. So it's the reciprocal of cosine, so it's secant. But if we come from angle B, then C over B is hypotenuse over opposite, and we know that's the reciprocal of the sine function, so that's going to be the cosecant. Okay, now look at this. The sine of one angle is the cosine of the other angle. The tangent of one is the cotangent of the other. The secant of one is the cosecant of the other. And how are these two angles related to each other? Well, let's think about it. They are the two acute angles in a right triangle. Now, all of the angles in a triangle have to add up to 180 degrees, right? And 90 of our degrees are right here. So that means 90 degrees are left for the sum of A and B. If A and B add up to 90 degrees, then that means A and B are complements. In fact, the way these three functions here got the co prefix on their names is that they allow us to talk about the function of the complement of an angle in terms of the original angle. This is exactly why the cofunctions were ever developed in the first place. So imagine that back in the day, you were a mathematician and you wanted to talk about not the sine of angle A, but the sine of the complement of A. Now, today we would probably just say sine of B, right? Because B is the complement of A in this diagram. But suppose you didn't want to drag another variable into it. You wanted to talk about the sine of the complement of A, but you wanted to keep the variable A there. So this happened frequently enough that instead of writing sine of the complement of A, they began to write comp sine of A. And then that got shortened even further to cosine of A. So you see the co in complement is the same as the co in cosine. It means sine of the complement of A. And so that's why these functions that have co in front of their name match up the way they do. And so here are our cofunction identities. It says for any acute angle A, cofunction values of complementary angles are equal. So the sine of angle A is the cosine of 90 minus A. Now keep in mind that 90 minus A is just another way of saying complement of A. So the sine of A is equal to the cosine of the complement of A, and it works the other way too. The cosine of A is equal to the sine of the complement of A. Same thing for secant and cosecant. Same thing for tangent and cotangent. I don't think you so much need to memorize these identities as you just need to understand how the co-functions work. So if you can just keep in mind that whichever function you're dealing with, the function of one angle is the co-function of the complement angle, then you've got all 6 of them and you don't have anything to memorize. So here we are in example 3, and we're going to get to practice with our cofunctions a little bit. And it says write each function in terms of its cofunction. So notice that they are not asking us to evaluate the cosine of 52 degrees. They're asking us to restate this in terms of its cofunction. So the cofunction for cosine would just be sine, and we know that whenever we change from a function to a cofunction, we change from the angle to the complement angle. So the function of an angle is equal to the cofunction of the complement angle. So how do we calculate the complement of 52? It's just 90 minus 52 degrees, and then we know 90 minus 52 is equal to 38. So now we can say the cosine of 52 degrees is equal to the sine of 38 degrees. And if you wanted to check this, you could totally pull out your calculator and get a decimal value for the cosine of 52 degrees, and that will be exactly the same as the value for the sine of 38 degrees, because 52 and 38 are complements, and cosine and sine are cofunctions. Now let's look at part B. The tangent of 71 degrees. We want to write this in terms of its cofunction. So the cofunction for tangent is cotangent. And then we want to find the complement of 71. So 90 minus 71 will be our complement angle. And we know that that's going to be 19 degrees. So now the tangent of 71 degrees is equal to the cotangent of 19 degrees. And then for part C, we want to rewrite the secant of 24 degrees in terms of its cofunction. So for secant, the cofunction will be cosecant. You know, you're always either putting the prefix co onto a function or you're taking it off. If you want to switch between cofunctions, you either add the co or you remove the co. So for secant, the cofunction is cosecant. And then we know that the secant of 24 is going to equal the cosecant of the complement of 24. So that would be 90 minus 24. And that's going to be 66. So the secant of 24 degrees is equal to the cosecant of 66 degrees. Now we're going to talk about the function values for what we call special angles. So two of our special angles are 30 and 60. So we're going to start by looking at an equilateral triangle, and we're going to make a right triangle out of this by just cutting this equilateral triangle in half. And when we do that, we get two triangles that are both 30, 60, 90 triangles. Now, since these sides were all labeled 2 units long, then when we cut this bottom side in half, each half is 1 unit long. So right now, we have a right triangle where the hypotenuse is 2 and one of the legs is 1, and we have not yet found the other leg, but we know that the angles are 30, 60, and 90. So now let's take this triangle and go over here to example 4, and we'll use this triangle to help us find the answers for example 4. And part A says, find the 6 trigonometric function values for a 60-degree angle. Now, in order to do that, of course, we're going to have to find the length of this unknown side right here that's opposite the 60-degree angle. And since this is a leg, and we know the length of the hypotenuse, we will want to use the Pythagorean theorem and subtract the squares of the 2 known sides, and then take the square root to find the length of the missing side. So 2 squared is 4, and 1 squared is 1. 4 minus 1 is 3, so this missing side is length square root of 3. Okay, now remember, we're finding the 6 trig function values for the 60-degree angle. So opposite the 60-degree angle is square root of 3, adjacent is 1, and the hypotenuse is 2. So now to get the sine of 60 degrees, we remember that the definition of sine is opposite over hypotenuse. So the sine of 60 is going to be square root of 3 over 2. And then the cosine of 60 degrees will be adjacent over hypotenuse. So that's going to be 1 over 2. And the tangent of 60 degrees will be opposite over adjacent. So that's going to be square root of 3 over 1, which of course just reduces to square root of 3. Now for the other three functions, we'll just use the reciprocal relationship. So the reciprocal of the sine function is the cosecant. So now the cosecant of 60 degrees is going to be 2 over square root of 3, but that needs to be rationalized. In other words, we have to remove the radical from the denominator. So we'll multiply by square root of 3 over itself, and that will give us 2 square root of 3 over 3. The secant of 60 degrees is going to be the reciprocal of the cosine, so that's going to be 2 over 1, which is just 2. And the cotangent of 60 degrees is going to be the reciprocal of square root of 3, so it's going to be 1 over square root of 3, which we will rationalize, and we'll end up with square root of 3 over 3. Now let's look at part B, where they've asked us to find the 6 trigonometric function values for a 30-degree angle. And we have the same triangle here to work with. So this time we're concentrating on the 30-degree angle. So the side opposite to the 30-degree angle will be 1, and the side adjacent to the 30-degree angle will be square root of 3, and of course the hypotenuse is still 2. So now for the sine of 30 degrees, we think opposite over hypotenuse, so that's going to be 1 over 2. And then for the cosine of 30 degrees, we think adjacent over hypotenuse, so that's going to be square root of 3 over 2. And the tangent of 30 degrees is going to be opposite over adjacent, so that's 1 over square root of 3. And then when we rationalize that, we end up with square root of 3 over 3, just like we did on the cotangent of 60 degrees. Now for the other three functions, the cosecant of 30 degrees is going to be the reciprocal of the sine, so that's going to be 2 over 1, which is 2. The secant of 30 degrees is going to be the reciprocal of cosine, so that's 2 over square root of 3, but that needs to be rationalized. And as you know, you multiply top and bottom by square root of 3, and you'll end up with 2 square root of 3 over 3. And then for the cotangent of 30 degrees, we know that's the reciprocal of the tangent of 30 degrees. Now, remember, if you take this rationalized number and you do the reciprocal of this, you'll have to do another rationalizing step. But if you take this unrationalized fraction, 1 over square root of 3, and do its reciprocal, you'll have square root of 3 over 1, and of course that's just square root of 3. So the cotangent of 30 degrees is square root of 3. And now we have example 5, and we'll be doing the same thing in example 5 that we did in example 4, except this time we're finding the 6 trig function values for a 45-degree angle. So here we have a 45, 45, 90 triangle, and notice that both legs have been labeled with length 1. So in order to find the trig function values for 45, we'll need to know the length of the hypotenuse. You know that according to the Pythagorean theorem, if we want the length of the hypotenuse, we add the squares of the legs and then take the square root of that. So both of these legs are length 1, and 1 squared is still 1. And so if we add the squares, we have 1 plus 1 is 2, and then the square root of that is square root of 2. So now we have the length of the hypotenuse is square root of 2. Now you can look at either 45-degree angle you want. Notice that for both of them, the opposite side is length 1, and the adjacent side is also length 1. So when we look at the sine of 45 degrees, we think opposite over hypotenuse, so that would be 1 over square root of 2. And when we rationalize that, we'll multiply by square root of 2 over itself, and that will give us square root of 2 over 2 as our final rationalized answer. Okay, cosine of 45 degrees, same thing. Adjacent over hypotenuse is still going to be 1 over square root of 2, and we still have to rationalize it, and we still end up with the same thing that we did for sine of 45 degrees. Now that makes a lot of sense because we know that the sine of an angle is equal to the cosine of the complement angle. And 45 is its own complement, so it makes sense that the sine and cosine should both be the same value. And then the tangent of 45 would be opposite over adjacent, so that would be 1 over 1, and of course that is just 1. And now let's get the other three functions. So we'll use our reciprocal relationships. The cosecant of 45 is going to be the reciprocal of the sine. So let's take this unrationalized version of the sine value and do that reciprocal. So now we see that cosecant of 45 degrees is square root of 2 over 1, which is just square root of 2. And then same thing for secant. The secant of 45 is also going to be square root of 2 for the same reason. And the cotangent of 45 degrees is going to be the reciprocal of 1, which of course is still 1. And so here we have all 6 function values for 45 degrees. Now, it is important for you to have pretty quick recall of these 9 values, the sine, cosine, and tangent of 30, 45, and 60. The better you know these values, the easier the rest of the course will be for you. If you have to fumble around and spend a lot of energy coming up with these values, then that's going to slow you down and make your job harder as we go through the rest of the course. So let's just invest a little time here in getting very familiar with these 9 values. I would say memorize them. Go ahead and memorize them. And if you're in my traditional on-campus class, you know you need to memorize them. So first, you'll remember from a couple of slides back that we found the sine of 30 degrees was 1/2. And because 30 and 60 are complements of each other, if the sine of 30 degrees is 1/2, then we also know the cosine of 60 degrees is 1/2. So sine of 30 degrees, cosine of 60 degrees, both 1/2. And then the cosine of 30 degrees was square root of 3 over 2. And because 30 and 60 are complements, the sine of 60 is also square root of 3 over 2. Now what about the sine and cosine of 45? They were both square root of 2 over 2. Okay, now before we do the tangent values, I want you to notice something here. All 3 of our sine values and all 3 of our cosine values all have 2 in the denominator. The sine values grow as the angle grows. So we start with 1 in the numerator, and then we have square root of 2, and then we have square root of 3. But the cosine values shrink as we go from 30 to 45 to 60 degrees. So we start with square root of 3 in the numerator, and then it goes to square root of 2 and then 1. Now tangent also grows as the angle grows. So we start with 30 degrees with a tangent of square root of 3 over 3, and then for 45 degrees we know the tangent was 1, and then for 60 degrees we know the tangent is square root of 3. So look, we go from a fraction with value less than 1 to exactly 1 to square root of 3, which we know is more than 1. Now I do have a set of Quizlet flashcards to help you drill yourself on these, and I really think it's a good investment for you to spend about 5 minutes a day for the next week or so drilling yourself on these 9 values. The more often you do it, the quicker you'll be able to recall the values. It doesn't take a lot of time, but it just takes a little bit of time doing it several days in a row. And now let's expand our 9 values into these 18. So we already know the sine, cosine, and tangent. Let's go ahead and get the cosecant, secant, and cotangent. So we know that the cosecant of 30 would be 2, the secant would be 2 square root of 3 over 3, and the cotangent would be the reciprocal of the tangent, so that's going to be square root of 3. Remember, this tangent value, before it was rationalized, it was 1 over square root of 3. So when you flip it over, it's just square root of 3. For the 45 degree angle, the cosecant would be square root of 2. The secant would also be square root of 2. That works similar to what we saw with the tangent and cotangent of 30 degrees. And then the cotangent would be 1. For 60 degrees, the cosecant would be 2 square root of 3 over 3. The secant would be 2, and the cotangent would be square root of 3 over 3. So once you have these 9 values memorized and you're very comfortable with them, then go to the next Quizlet deck and throw in the reciprocal functions and drill yourself on all 18. So there is a Quizlet deck in Canvas for you that has just these 18 values. And again, the better you know these and the more quickly you can recall them, the easier things will be for you going forward into the next chapters. And that's it for section 2.1. As always, practice, practice, practice in my lab in Quizlet, and I'll see you again in the next section. Bye now.